In order to do thermodynamics, we require a very strong foundational understanding of what entropy is, because entropy is one of the most important determiners of whether or not a process will happen spontaneously. So what entropy is, colloquially, we think of it as the disorder of a system, but actually it's these specific ways that you can arrange a system. And it happens to be the case that a more disordered system has more ways that it's possible to arrange it. So we're going to distinguish between the macrostate of the system, that's sort of the general look of the system, and the microstate of the system, which is the very specific arrangement. So for example, you might have a clean room or a messy room. So those would be two macrostates describing your room. The microstates would be all the different ways that it could be clean or all the different ways it could be messy. So to be clean, maybe you can take your books and organize them by author, or maybe you can take them and organize them by subject, still organized. A messy room, your dirty socks can be strewn anywhere, and it's still a messy room. So those would be individual microstates, but the same macro state. So for an example, in which we're going to try and depict some molecules, we might consider a system where we have 12 possible positions, maybe in a crystal of some kind, and we have potentially 8 blue molecules and 8 red molecules. And let's say that by unmixed we mean that half of our box is red and the other half is blue. So in that case, there's 4 possibilities depicted here. So these are our 4 microstates, and each of these microstates describes an unmixed system. Now our mixed macrostate, that's basically any other configuration of our system. And as you might imagine, there are lots and lots of different ways that we can have a mixed system. Now if you take a few steps back and you look at these systems, you probably don't really distinguish between them. They all look the same to you, a jumble of red and blue. And so in some cases, it doesn't really matter which one of these is in, we'll just say that it's mixed. But if our systems can occupy any of these configurations, what are we more likely to see if we look at the system after some random time of evolution of the system? Well, I think it's pretty clear that we're going to observe the mixed macrostate, because there's so many more possibilities which are mixed. If we just look at some random possibility, it's almost guaranteed it's going to be one of the mixed ones. And for large systems, where instead of having 16 possible molecules, we have Avogadro's number, which is 6.022 times 10 to the 23, then it becomes a certainty that we're going to observe one of these mixed states. As another picture, let's say we have this kind of odd container here. It's filled up with water, and it also has, say, a sodium ion in it. Now I think it's pretty obvious that if we stick the sodium ion over here, it's going to at some point drift over here, and once it drifts over here, it's more likely to drift over to this side than to this side, because we have more possible ways that it can do that. Now as we increase the volume of the water, the ion is going to spend more time wandering around in that volume of water before it can find these boundaries. And I think it's probably intuitive that it's eventually going to progress over here, and it's going to spend a huge quantity of time over on the right side, compared to the very small probability that it would actually make it back over here and spend a little bit of time in this volume of water, which offers very few possible positions compared to the great number of possible positions over here. And we might even consider connecting this to another reservoir of substantially larger size, say the Pacific Ocean. Now, do you think if that salt ion wanders around for 1 billion years, that when we check back on it, we're going to see it over here in this little, maybe 10 molecule droplet. No, we're not. We're going to see it somewhere in the Pacific Ocean. This basically describes the evolution of the universe. The universe starts off very ordered, for example, having all of your energy inside of a star, but then that energy disperses, and there's really no way to get it back into that ordered state. Once you get into the very wide-ranging possibilities of this ordered state, you're going to stay there, just like our ion in the Pacific Ocean. So in general, when we have the option of being in systems of higher entropy, we are going to progress through those systems into the very highest entropy system. And so our systems are going to evolve and increase in entropy. Now we might have a different setup. We might just have the ion trapped in this volume of water here, in which case there's no real way for it to increase in entropy. It has a fixed entropy in this case. So we can also have a system where the change in entropy is just going to be nothing. It's just stable, no alterations are occurring to the system. So this, in essence, is the origin of the second law of thermodynamics. The entropy of an isolated system is going to either increase or remain constant. And this isn't truly a law. It is technically possible that our ion could drift back into that very low entropy region, but once we're talking very large systems, Avogadro's number worth of molecules, that probability is so vanishingly small that essentially over the lifespan of the universe, it's just not going to happen. So we call this a law. We would actually like to be able to quantitatively use this information about entropy and make comparisons and predictions. So there is a mathematical way of expressing entropy, which we represent with our capital S. And it's going to be equal to Boltzmann's constant times the natural log of the number of microstates, the number of configurations of our system. And the reason we take the logarithm is because these numbers are so big that in order to realistically treat them, we really need to take the natural log, convert it to a logarithmic scale. And then we have Boltzmann's constant, which is 1.38 times 10 to the minus 23 joules per Kelvin. And this gives our entropy value physical units. But really, entropy is just counting the number of configurations. And this is just kind of a special way of expressing that. So, for example, let's say we want to find the entropy of this system if these molecules can freely swap their positions. So this red molecule can wander around this box over here. Well, there are 9 different configurations in that case. It could move over here and trade positions with this molecule, or this one, 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 or it could remain in the same spot. There's 9 possibilities. So we have 9 microstates. So we're just going to plug that 9 in for W, that represents our number of microstates, take the natural log of it, and then multiply by Boltzmann's constant, and we get an entropy of 3.0 times 10 to the minus 23 joules per Kelvin, which is a very small entropy for a very small system.